Hi everyone. I want to go over some ideas in the worksheet that I gave you on work. For each question, I'm just going to go through a few hints, things that should hopefully help. And if you have done the questions already, it could be really useful sort of insights or little details that will help you with other similar questions that you might not have thought of while you were doing these. So let me pull up the sheet. So that's the one. The questions don't really appear in the first sheet for some reason, but I've labeled this one as question 1, the one with the boat is question 2, question 3 is the one with the weightlifter, question 4 has the dog, question 5 has the skier and the slope, and then the next sheet that's question 5 here, and that would be question 6 with the skier and the slope. And so next sheet is question 7, and those are numbered. Okay, so I'm going to try to go through these. Hopefully it will be like 2 videos, maximum 3, to go over the hints that I want to go over. And so let's start with question 1. So there's a lawnmower and somebody's pushing it 80 meters along, and they ask you for the work done by the person pushing and then the work done by the friction. So here's my bad diagram of a lawnmower, and the forces acting on it are the force of the push of the mother who's cutting the lawn, and then the force of friction. They tell you that it moves 80 meters, so they give you the distance, and they ask you for the work done by the force of the push. And that's really easy because the forces, you can assume it's in the same direction because they don't give you any weird angles or anything, so you just do the usual formula for the work done, which is the force of the push times the distance moved, right? So that's easy enough. In the second part, they ask you for the work done by the friction, and in order to calculate the work done by the friction, you need to know what's happened to the energy. And they tell you in the question that in the part B, they tell you that the lawnmower has no kinetic energy when she's finished the task. So that means that all of the kinetic energy is used up. So if the kinetic energy has been all used up, it means it must have gone into somewhere, and since it's not going up a slope, it's not going into potential energy, so it needs to it's gone into resistive, to friction and heat and other forms of energy that are the cause of the force of friction, right? If there wasn't any friction, all of the work that she's doing would have gone into kinetic energy, so that when she lets go, it would have just kept on going with the kinetic energy equal to the work that she's done. But since there's no kinetic energy, it's all gone into friction, so we can assume that all of the energy is being done, it's been taken away by the friction. So then the force of friction is also applied during the whole of the 80 meters, and the work done needs to be the same as the increase in as the work done by the she's done, because no kinetic energy is left and no potential energy is left. So that means that the work done by the friction, so this is the work done by the push, and the work done by the friction is going to be exactly the same as the work done by the push, except if you look at the direction of the force, it's opposite to the direction of motion, right? The direction of motion is that way, and the direction of the force is to the left. And the definition of work done is force times the distance and the force in the direction of the increasing distance. So here, since they are opposite, then you have a minus sign, and instead of plus 8,000 joules, you end up with a minus, so a negative value for the work done. So hopefully that explains the negative in the part B. Question 2 is about this boat being tugged along, and they first ask you to get the force in each cable and to chop it up. So this cable, they tell you has 36 kilonewtons, so don't forget to put it in times 10 to the 3. newtons, and this cable also has 36 times 10 to the 3 newtons. So they ask you to each cable to chop it up into the parallel and perpendicular directions to the motion. So what's the parallel direction to the motion? Well, the whole thing's moving in that direction, so parallel to the motion would be the component of that force which is going along that direction, right? And since that's 26 degrees for the full angle, then we only need to really look at half the angle, which would be our 15 degrees. Hopefully that makes sense. And so they're asking us to chop up this force into the two components, so for each cable. So let's look at this cable first. The other one's going to be exactly the same, but since they're both symmetrical. And so here we have a triangle that looks like this. This is 15, this is 36 times 10 to the 3, and this is the horizontal component, so the parallel component of it, and this is the perpendicular component, and they ask you to calculate both of those components. So hopefully you know how to do that already. That's the hypotenuse times cos of 15 would be the parallel one, and sine of 15 would be the perpendicular one. You should get those two values pretty easily. Which way is this one gonna go? Well, it's gonna go to the right, because this guy is mainly going to the right, and this one's gonna go up because it's also pushing it slightly up. With this one, it's the opposite. This one goes still to the right, but the vertical component would be down instead of up. Hopefully that makes sense. In the second one, they ask you for the work done in pulling the vessel 2 kilometers. So now they tell you the distance, which you need to know, and they ask you for the work done by the forces parallel to the motion and then by the forces perpendicular to the motion. So what they're trying to get you to do here is, in the first one, it's pretty easy because you started with a force going in that direction, but the motion was going in this direction. So you wanted to know that component when you knew that this was 15, right? So how much is the work done in pulling the vessel? So that means by the two components, right? So by the two cables, right? So the work done is going to be both forces times the distance. So they tell you it's 2 kilometers. So this is moving a distance of 2 kilometers, which is 2,000 meters. You always need to put it in meters. And the force is whatever you calculated before, so that should come out to be 35 kilonewtons parallel. So if this was 36, then along here it's a little bit less because not all of it goes along this direction, so it's 35 kilonewtons, but there's two of those cables, right? So in total the force going in that direction is going to be 70 kilonewtons, and the distance is 2,000, and they're in the same direction because we've taken this component of the force, so now we're fine. We can work out the work done in that direction, and that's easy. Now the slightly trickier part to understand is part B. In part B they ask you to find the work done vertically. So you've already chopped up this force into your vertical in that direction and your vertical in this direction, and the truth is that if the boat is moving along this line, then there's no movement whatsoever up or down. It's completely the movement in that direction. So if you're going to look at the work done by the perpendicular forces, the reason why the answer here they give you 0 is because there's no distance traveled at all in the vertical direction, no distance in the perpendicular direction. Okay, that's really important. That's why when you do the work done is equal to the force times the distance comes out to be 0 because it's not moving up or down, so then it doesn't matter how big the force is, the work done is still going to be 0. Okay, so in other words, another conclusion of that, which is a little bit strange, sometimes people find this, I definitely found that a bit weird when I first started thinking about work done, is that even if you're putting all your might into pushing really hard onto a wall, yeah, and the wall is not moving, there's no movement at all of the wall, then even if you're sweating and you're putting all of the effort in the world into it, you're doing no work. Okay, you're doing no work whatsoever. Not in the physics sense of the word work. Okay, so if there's no it's really looked at as nearly as a useful thing. So there's no work if there's no distance moved. Okay. Now, notice that if the wall was moving in that direction, say it moves 10 meters, and I'm still pushing in that way back on the wall like that with like 100 newtons, then I am doing work in this case, but now it's 100 times 10 times 10, which is 1000 joules of work that I'm doing. But since the force I'm putting in the direction that the wall is moving is opposite, then I need to put a minus here. So actually, even though I'm trying to do work, I'm doing negative work on it. Why? Because I would be removing energy away from it, right? If it comes with a kinetic energy of so much and it's traveling along, and I'm doing this work on it of 1000 joules, then that 1000 joules is energy I'm going to remove away from the wall's kinetic energy if it's moving in that direction, opposite to the one I'm pushing. The same way as here with the lawnmower, this work done by the friction was negative because it was removing away, it was removing all the kinetic energy that the lawnmower would have had if there was no friction. It definitely removed all the energy that the mother put in with the work done of pushing. Okay, hopefully that makes sense. And let's move on to question 3, which I think will be the last one before we have to pause the video because we're running out of time, and then we'll go on to the next one. Let's see, question 3 is the guy with the dumbbell. So he says he lifts it 60, it's a nice little space here to do the question. So he lifts it a distance of 0.6 meters, that's 60 centimeters, and he produces he produces a pull of 3,800 newtons, and the mass of the barbell was 240 kilos. So the work done by the weightlifter on the barbell. So for the work done that he does, it doesn't really matter at all the weight of the thing. What matters is for the work that he does by the weightlifter, what matters is the force that he applies, which is the one they give you here, and the distance through which he applies it. So really it doesn't matter about when you're doing work done, what matters is what's the force, how much is the point of application moving. Those are the two things that matter. It's not about resultant forces like in second Newton's law or acceleration or anything like that, where you need to cancel out the forces and see what's left over. When it's work done, you don't care how heavy the thing is, you care this is the work that I'm doing, this is the force that I'm putting, and I'm moving it this distance, and that's the work that I'm doing. When this matters is to see how much energy is left in the object after I do that work. Maybe I can, you know, I have a lot of motion left, or maybe most of it is being taken away because of the work done on it by gravity. So then it will be important. But when you just need to know the work done, then you just have to multiply those two. The work done by the pull of the earth on the barbell, then you need to know the force applied by the pull of the earth, which is the weight. So for part 2, you need to know the weight of the thing, which is 240 times 9.8. That would be the weight. In other words, it's a force applied by gravity, and that force applied by gravity is through that distance also. So that's the only distance that the thing is moving. So by multiplying those two, you can then compare the answer with that one here, and they give you the answers here. One of them is 2.3 thousand joules, the other one is 1.4 thousand joules. So there is a difference. In other words, the weightlifter does more work on the barbell than gravity does. So therefore, this difference is gonna, since they don't talk about friction or anything like that, the difference is gonna be in the form of kinetic energy left in the barbell. So by the time it gets up to 0.60 meters, it's still moving with some kinetic energy. That's what they're trying to get you to understand in the question. Okay, so running out of time with this video, but hopefully this makes sense. The idea that the work done is just the force applied times the distance, and then the difference between them two only comes into we only care about it when we want to know what happens to the energy that's left. Is there any energy left, or is the thing moving still or not? But in terms of work, we just calculate the absolute values. So this is the amount of work that Wade did, came out to 1.4, and it was less than the one that he did, so some energy was left in kinetic energy. Alright, see you in the next